The burning of fossil fuels are significantly increasing the concentration of CO2 in the atmosphere, thus contributing to Earth's global warming. However, the world will continue to rely on combustion of fossil fuel in the coming decades. Thus, we are motivated to mitigate CO2 levels using different technology, including CO2 capture. To support CO2 mitigation, captured CO2 can be stored underground in deep rock formations and depleted oil reservoirs. The main problem preventing large-scale carbon capture and storage adoption by power plants is that the technology is very expensive and largely unproven. A promising way to mitigate CO2 would be to capture CO2 and convert it into useful chemicals and fuels through hydrogenation. A potential material is metal organic frameworks, commonly called MOFs. MOFs are a class of crystalline porous material that have extreme high surface area. This makes MOFs a good material for gas capture and gas separation. MOFs are synthesized by self-assembly of metal ions and organic linkers. We use MOF UIO66 as the candidate because it is stable and can be functionalized. Mimicking the MOF synthesis, the catalytic moieties of CO2 hydrogenation can be anchored on the organic linker through different methods, such as post-synthetic modification or post-synthetic ligand exchange. In this way, functionalized MOFs can be used as a heterogeneous catalyst for large-scale industrial processes. We have tested the reaction, CO2 hydrogenation, to produce formic acid, which has two elementary steps. Step 1 is to dissociate the H2 molecule. Step 2 is to hydrogenate CO2 to formic acid. We have screened a variety of functional groups following the same reaction pathway and constructed a microkinetic model to estimate the activity of the catalyst. Along these lines, we can screen hundreds of different functional groups. We can also screen different MOFs. Instead of performing thousands of experiments to test the activity of these catalyst candidates, we have instead performed computational simulations first to predict the best candidates. Using the best candidates materials from simulations, we will synthesize and then pack them into portable reactors. These reactors will then be installed at the sources of CO2 production, converting CO2 to useful chemicals and fuels, closing the anthropogenic carbon cycle.